Thank you very much, Lerande, for the warm welcome. Thanks to everybody for joining for the very first session. It's my great pleasure that I get to start off the conference and start off the tutorial day. So as you just heard, my name is Matthias. I'm an assistant professor in computer science at the University of Warwick. And today I'll tell you a little bit about essentially some recent fascination of mine. So I'll tell you about how we can go beyond just learning theory by bringing in ideas from testing and verification. So my goal for today is that after this tutorial, you believe me that these are interesting questions that learning theorists should ask, in addition to the questions that we ask anyways. So before I actually start, let me check two things. First, can you hear me in the back? Everything good with the mic? Okay, perfect. And second, whenever you have a question, please do ask. My material will not fill 90 minutes, and I want you to ask questions along the way. In particular, what I'll do today is I'll try and tell you about questions, like research questions that one can ask, and about essentially perspectives that one can take. So if something about this is unclear, please do stop me and ask, because probably it's unclear to not just you, but many others in the room, and then I can try and explain again. All right, so let me get started. What I'm going to talk about today is the following. One sec. Okay, I'll fix the clicker in a second. What am I talking about? So essentially, what I'm thinking about is the quantum learning workflow, which looks as follows. Perfect. Thank you. So in every machine learning problem, be it classical or quantum, you have to start with data. Because we're in quantum learning theory, our data is often copies of some quantum state that you want to learn something about. But also if you're a classical learning theorist, or if you're using variational quantum machine learning for classical data, your data might just be classical samples. Then what we do is we feed that data. Okay, I just have to point in the right direction. We feed that data into a learning algorithm. In quantum learning theory, the learning algorithm often starts with the measurement. After the measurement, you have some classical post-processing, and that whole thing makes up your learning algorithm. Okay? And then after that learning algorithm, you end up with a hypothesis. If you consider some state learning problem, for example, tomography, you would end up with an approximate state. If you consider some function learning problem, you would end up with an approximate function. So this is roughly what the quantum learning workflow looks like. What I want to emphasize today is another implicit ingredient, which is assumptions. So in almost any learning problem, we make assumptions about the unknown object or the representation we choose. For example, you might assume that the quantum state is from a specific class, say stabilizer states, matrix product states, something like this. Or you might assume that the function has a nice structure. If you have spent some time with variational quantum machine learning, you may be familiar with the Fourier expansion for these models, and then you might want to make some assumptions about them having few relevant frequencies or something like this. And what I want to emphasize today is that these assumptions are really crucial in quantum learning. Why is that? So quantum learning can go really wrong if we have a few potential breaking points in this workflow. So the first breaking point that I want to highlight is just the final one. So when we produce one of these hypotheses, if you're a learning theorist, you want this to be probably approximately correct. So this means that with high success probability, you want to output something that is close to the truth. We don't always know whether this is the case, and this is something we might want to check. That's breaking point number one. Breaking point number two is whether, even though you might have the right quantum learning algorithm in mind, whether you're executing it correctly. This is in particular relevant in an era where our quantum devices are faulty. So how can we check whether quantum learning is executed correctly along the way? Okay, and I'll highlight two more. So the next breaking point is whether assumptions are satisfied. Right? So if we design learning algorithms with assumptions in mind, what goes wrong if the assumptions aren't satisfied? Or can we make sure that the assumptions are satisfied? And then finally, and this is, I think, maybe a little bit of an unconventional breaking point, you should also worry whether your data has been correctly collected. So what I mean by this, for example, is that if you imagine that you're getting copies of a quantum state, this quantum state might be corrupted by noise. And then you also have to worry about what this corrupted data, what this means for your learning down the line. The plan for today is that I'll go through some of these breaking points and tell you how you can use techniques from other areas of computer science to address them. Before I do so, questions about this hopefully not too confusing slide? Okay. Yeah, Adrian, please.
Why is it that, why would you like to ask what happens if your assumptions are not satisfied?
Yeah.
In every single framework in computer science or linear theory, the assumption doesn't work, it doesn't apply.
Yeah. Very good question. So what do we do when assumptions aren't satisfied? I think I'm mostly with you. We can't say much about assumptions not being satisfied. So let me rephrase. What I actually want to do is I want to design an algorithmic framework for checking assumptions, so that you don't just make assumptions because you make an educated guess, but you have an algorithmic way of certifying assumptions. Thank you. Okay, further questions? All right, then let me continue. So I've divided this into 3 pieces. First, I'll tell you about how to test assumptions of quantum learning algorithms using the framework of property testing. Then I'll tell you about how to verify the process of learning using interactive proofs. And finally, I'll tell you a bit about testing the outcomes of quantum learning using something called identity testing. I'll sprinkle in some of my own work, but most of what I present is not my work. It's work that's been done by lots of people over the last years. And essentially my goal is to inspire you to take a closer look at some of these works and to give you an overview of the questions they ask and the results they prove. So let me start by talking about testing assumptions of learning. So here I'll focus specifically on this breaking point. So the potential breaking point is if assumptions are unsatisfied, learning algorithms may fail. So how do we check these assumptions? And now, okay, this probably everybody knows. I just want to make sure that I say it once. You need assumptions in learning. In classical learning theory, this is known as no free lunch theorem, or if you want, no free lunch theorems, because there are different formulations of it. And essentially what these tell you is if you don't make structural assumptions, no efficient learning is possible, from an information theoretic perspective even. So you just need too many data points. And while I could show you classical versions of this, because this is a quantum conference, let's focus on quantum learning examples for this. So the most commonly cited example for a no free lunch theorem in learning, even though it's not called a no free lunch theorem in learning, is the complexity of full tomography for arbitrary mixed n-qubit states. So it's well known that this requires an exponential complexity. In particular, we know by work by Ha et al., O'Donnell and Wright, and a more recent paper also by Wright and his group, that this requires 4 to the n over epsilon squared many copies if you want to perform tomography to accuracy epsilon in trace distance of an arbitrary mixed n-qubit state. And this is infeasibly large. So for most intents and purposes, you cannot do this. So what people have done instead is to consider assumptions and how these assumptions may help you make tomography better. The first assumption you could make is just assume that it's a rank R state. That already brings the complexity down a little bit. You still have an exponential factor, but at least it's not the same exponential anymore. So we're gaining a little bit. Or you could make even more structural assumptions. For example, if you assume that it's a stabilizer state, the complexity of tomography suddenly goes down to linear in system size. This is a result by Montanaro. Similarly, if you assume that the entanglement structure is nice, by assuming that it's a matrix product state with a small bond dimension, you get a scaling that's polynomial in system size, and it depends on local dimension and bond dimension. Or you can also restrict the circuit complexity of these states, and again, you get improvements in the complexity for tomography. If some of these words don't mean much to you, don't worry. I'll explain the ones that I'll talk more about during the talk. But the point is that we go from no assumptions and inefficient learning to imposing some assumptions to make learning efficient. And what I want to do is tell you a little bit about certification of such assumptions. So to do this, I'll introduce property testing, and I'm not going to be particularly creative, so I'll introduce it with the same picture that everybody uses. My apologies. It's sometimes called the egg yolk picture of property testing, and you'll see in a minute why. So property testing is roughly the following. We start off with a full space. This is the space of all possible objects that we could care about. So it could be the space of all possible functions, could be the space of all possible quantum states, or whatever other space you might care about. Now, in this full space, there is some subset that we think of as nice. This could be functions that can be represented with states that can be implemented with short quantum circuits, could be stabilizer states, could be functions that can be represented by using only a few terms in the Fourier expansion, whatever you like. And now in property testing, essentially we want to find out whether we're in the nice set. Unfortunately, you can't solve this question in general. So what we instead do is we introduce a margin of error. So we put a circle of radius, I guess we allow ourselves to be epsilon away from our nice subset. Everything outside this ball we will think of as a not so nice subset. So that's where you don't want to be. And this is what in property testing you want to distinguish. So are you in the yellow egg yolk, or are you outside in the red not so nice subset? This is also where the egg yolk analogy breaks down, because if you have that much red in your egg, you probably shouldn't eat it anymore. But that's roughly what property testing looks like. Okay? So the crucial ingredients are you have a nice subset that you would like to be in. This is the assumption that you're trying to certify. And you want to find out, are you in that set, or are you far away? Questions about the picture? I'll give you some math in a second. All right. So then let's do the math. So how do you actually define property testing? I'll go for a very abstract definition here. I'll make it concrete with examples. The reason I'm going to give you the abstract definition is because we want to apply it to lots of different problems. So if I give you a concrete one, I have to give you a new definition every time. So the abstract way of framing property testing for some property P is the following. So you start from a property, and the property is just a subset of your space. So again, this is the subset of nice objects. In addition to that, you need some kind of distance measure. Don't take this too literally. It doesn't necessarily have to be a metric in the mathematical sense, but think of it roughly as a distance measure. Okay, and then we need two more things. So the first is that we need an accuracy parameter. So we have to say how far away from the property is too far. And finally, we also need to specify how we get access to the unknown object. Okay, so to give you some example, because this is a little bit abstract, in quantum computing this could be getting copies of a quantum state, getting access to a quantum circuit that prepares the quantum state, or if it's a quantum channel, you get access to the quantum channel where you can feed in whatever you want and you perform a measurement at the end. Those would be typical examples. Okay, and if you're given all this, property testing is a decision problem, and you're supposed to decide between two alternatives. Alternative one is the unknown object is in your property. So the unknown object is nice. Alternative two is the unknown object is epsilon far from your property, which means that the distance between the object and your property, and this is just defined as the minimum distance between the unknown object and anything in the property, is at least epsilon. Okay? So these are the two cases that you should distinguish. Does every x satisfy one of these two cases? Yeah, correct. So not every x satisfies this, so I have to put in an extra assumption, which is you should do this promise that either one of the two is the case. So, and by the way, sometimes you can do this with probability 1, but it's extremely rare. So let's look at some success probability, say 2/3. As always, the success probability doesn't matter. You can easily increase it by repeating and doing majority vote. Okay, so just to clarify, going back to the picture, in this region in... Yes. In this white region here, you can view it in two ways. Either, I promise you, I'm never going to ask you about an object in this white region. Or you can think about it as, if I ask you about an object in the white region, it doesn't matter what you answer. This is essentially necessary for the problem, because if you allow objects here that get arbitrarily close to the property, it becomes very hard to distinguish. So that's why it's important to have this margin epsilon here, and that's why it's also important that in this annulus around the property, we don't care about the answer. Okay. Okay, this is the thing that I said before. So Oracle access to an unknown object can mean many things. Can mean samples, queries, copies. Yes, please.
Yes, can I ask, so by defining the property as a subset, aren't we kind of jumping a step? Like this would be the instances in your space that meet the property.
Yes.
Wouldn't it be like a function of that, which implies that your epsilon is defined on the application of this property and not in your space?
So you're saying
Totally incongruent.
I'm not quite sure whether I understand what you mean by the application of, but what you could definitely do is you could define the subset indirectly. So you could, for example, instead of taking a set of states that have some property that you would naturally formulate in terms of states, you could also define it as a property of, say, states that evaluate to a certain expectation value for a given set of observables or something like this. So you could indirectly define it. I think it's common to think of it as a subset, though. I don't know whether there are other options. Maybe there are. Do you have an example in mind, maybe?
No, I'm trying to think because when you define it in this way, the epsilon is kind of regular in your space, right?
Oh, yeah.
The epsilon is the application, is application.
Oh, yeah, sorry. Now I understand what you're saying. So you're right that kind of the way I drew it, the epsilon is kind of nice and uniform in the space, but you could essentially change this by changing your distance measure. So if you take a standard distance measure like a Euclidean distance, then it looks like I drew it, but you could take a super weird one, and then you could show more complicated behavior. Good question, thank you. Okay, other questions about the definition of property testing? All right, good. Then let me show you one variant that's important. I unfortunately won't talk about it too much today, but I have to say that it exists because otherwise I'd be leaving out an important part. And this is called tolerant testing. So in tolerant testing, you start with the same picture, so you have your egg yolk, but you essentially make a slightly, you allow for a slightly weaker assumption in that you're not going to require your unknown object to be either in the property or far. Rather, you allow it to also be close to the property. So, oh, this is not readable. This is supposed to be an epsilon 1. So you have like a radius epsilon 1 around your property that you still consider good. And then around that, you put another ball. So you separate it from another larger radius epsilon 2, and everything outside epsilon 2 you consider bad. This is important because often it's hard to argue why an object would exactly have a desired property. Maybe you only have approximately the desired property. And then you should consider tolerant testing. Tolerant testing is relatively easy to see, is essentially the same as distance estimation. So testing whether X is close or far from a set is roughly the same, up to some logarithmic overhead, as estimating the distance to the unknown set. So if you care about distance estimation, you now know that it's essentially a problem like tolerant property testing. As I said, I unfortunately won't talk about it much today. Often, tolerant property testing is the more realistic variant. Unfortunately, it's also often quite a bit harder than standard property testing. And for simplicity, I'll focus on the standard one mostly. Okay, so I'm trying to make this interactive, so I prepared quizzes. Let's see whether this works. So quiz 1 is the following. And I apologize, I spent a lot of time in my life studying classical learning theory, so sometimes I give classical examples. I know this is a quantum conference, but hopefully you still like my classical examples. So let's consider a property that is a property of functions that map, say, n bits to a single bit. Okay, so this is some subset of the space of all possible functions. And now I have to specify the other ingredients. So for the distance measure, let's take the disagreement probability, meaning the distance between f and g is just the probability that f and g disagree on a uniformly random string x. Okay. Let's also take some accuracy parameter epsilon, and I have to specify the access. So my access model to f will be via IID random samples. Okay, so you can query multiple times. You can collect these IID random samples, xi, f of xi. This now specifies a property testing task, according to what I said on the previous slides. And my quiz question is, please describe for me an algorithm that solves the corresponding property testing problem from a number of samples that scales like log of the size of the property over epsilon. And what I'll try is come up with that algorithm together with you. Let's see whether that succeeds. And then we'll discuss what this result tells us. All right. Do we have any ideas? How could we try and test something like this? Notice that the weird thing is that I'm not even telling you what the property is, right? So some of the algorithm has to be very generic. We're not using any structure of the property. Any ideas? Let's maybe start with a special case that's a little bit easier. Suppose this property here is only a single function. Okay, suppose there's some kind of f0 and we want to check, are we f0 or are we at least epsilon far from f0 with respect to disagreement probability? How would you check that? Any ideas? Yeah?
Sample inputs and compare to what the target function does.
Yeah, exactly. So let's just draw a random sample x, and if the label f of x that we get disagrees with the label that f0 assigns, then we already know it can't be f0, right? Because it disagrees. So the only question is how many samples do we need to see one that disagrees if the function is far? And you can hopefully relatively easily convince yourself that this would be like roughly 1 over epsilon samples, right? So because essentially we're assuming that the distance between the two functions is at least epsilon. So that means that the probability of sampling an x that disagrees is at least epsilon. And then it's just kind of a geometric probability thing. So you have to check, okay, how many samples until we have like constant probability of seeing this. And that would be 1 over epsilon. So you really just check whether you get a sample that violates the property. Okay, now the next step is how do we get from a single one to the whole set, to the whole property P? Any suggestions?
Sorry, I have a question.
Oh yeah, please. A subset. A subset. So a property is just a subset of the space. No. So this is the point of the quiz. There's a kind of a trivial upper bound that works even for unstructured properties. As you see, the bound that I show here is useless if your property is infinite. And if your property is very large, it's still pretty useless. So that's kind of the point of the example. If your property is small, then there's a trivial algorithm that tests it without taking the structure into account. Thank you. Okay. Any ideas for how we can go from 1 over epsilon for a single property to log property size over epsilon for a generic property? I promise it's not complicated. Yeah.
Okay, if it's log, you're going to have to do some judicial divide and conquer. So can you isolate it into individual arguments?
Good idea. So logarithm suggests that there might be some divide and conquer going on. In fact, it's stupider. Sorry, I'm not using anything clever. We're only going to use a union bound here. So this is all that I'm using in this argument. If you check the dependence on the target probability, you will see that it depends like log of 1 over target probability. If you've ever done one of these probability calculations, it's always log 1 over delta, so this probably doesn't surprise you. And then essentially you just do the test for every single element of P in parallel. So for every function in P, you just check whether you disagree with that function. And you do all of this in parallel, and because of the logarithmic dependence on the success probability, you're fine. Does that roughly make sense, or should I try and write something down? Yeah, Adrian?
This logarithmic 1 over delta is rooted somehow in the Chernoff bounds.
Yeah, so in this specific case,
The Chernoff bounds are always applicable.
So in this specific case, you don't even need a Chernoff bound. There's a pen. Okay, so suppose that you have that the distance of f and f0 is at least epsilon. This is the far case. That means that the probability, if you sample an input, that you get something that disagrees is at least epsilon. So if you want the probability of, let's say, f of xi is f0 of xi, and you want that for all of your samples, because these samples are IID, you can upper bound this probability. So this is actually, yeah. You can upper bound it like this. So the 1 minus epsilon comes from the assumption that the disagreement probability is at least epsilon. And then it's just IID samples, so you get the power. And now you see where the log comes from, right? Because the m is in the exponent here. So if you want this to be equal to some delta, you rearrange and you get an m that depends logarithmically on delta. So here you don't even need concentration bounds. It's even more basic. Okay. So let me get back to the question, which was a very insightful one. So in this quiz, I've not used anything, right? I've just given you an arbitrary subset, and we've designed the property testing algorithm. So, okay, we could, of course, be very proud of ourselves for designing this property testing algorithm, but in some sense, it also shows us that this can't be the way to go, because we've not used the structure of the property. So this cannot be a good algorithm, and in fact, for many properties, this will scale horribly. So the number of functions from n bits to a single bit is 2 to the 2 to the n. So we can find subsets that are extremely large and where this bound will be very bad. So the rest is about finding better bounds. And one way of getting better bounds in property testing is actually to use learning. Oh, sorry, Manuel.
Very good question. How is this bound compatible with the complexity?
So it's compatible with the complexity for learning mixed states because, so first of all, I'm not making a statement about learning here. This is just testing, which is weaker. Even then, if you use this for mixed states, you will mostly get trivial bounds if you apply it directly, because most of our sets of states are continuous. You could apply it to some discretized version of the states, and then you would get some bounds. Most of them won't be particularly good. But the main reason why this doesn't contradict anything in learning is because it's about testing, which is an easier task. Okay, so one way you could do testing better than what I just showed you is use learning. So I won't show you the proof, but I'll show you the picture, which is the proof. So how can you do testing by learning? We have to distinguish two cases. We have to distinguish the case where we're far from the property from the case where we're in the property. Let's start with the case where we're far. So let's suppose we have an x somewhere outside that epsilon ball. Now we run our learning algorithm, but suppose we have a learning algorithm that only works for points in P and always outputs something from P. So for example, you have like an algorithm that learns matrix product states with a certain bond dimension, and you promised it always outputs a matrix product state with that bond dimension. But the state that you're running it on just has no good MPS representation. Well, you're still going to output an MPS with some bond dimension bound. So you're still in your property. Even though you have no guarantees for your learning algorithm, the one guarantee you have, if it's a proper algorithm, is that it's in your property. And then if you know how to estimate distances, you can estimate the distance between your hypothesis and the unknown object. And you will see that this distance is larger than epsilon, because the unknown object is out here. In contrast, if you start from a point that's in your property, and you run your learning algorithm, because it's in the property, you can run your learning algorithm with an accuracy guarantee. So for example, you can run the learning algorithm with a parameter that's good enough to guarantee, say, distance at most epsilon over 3. And this is your distinguishing algorithm. So you check, is your distance smaller than epsilon over 3 or bigger than epsilon? Okay. Now, this is somewhat useless. I've introduced testing to test assumptions of learning, and now I'm using learning to solve testing. That doesn't make much sense. This is just the demonstration that testing is in fact easier than learning. Is no harder than learning. Now the point is that you can do better. You can in fact do much, much better. And what I'll do now is I'll show you without a proof the kind of canonical and most important example. Okay, let me take back the most important. One of the most important for where testing can be better than learning. This comes from classical computer science, and it's called low-degree testing. So in low-degree testing, you have some degree that you would like to test, some accuracy parameter, and query access to an unknown function. And you're supposed to decide whether that function is a low-degree polynomial or whether it is far from all low-degree polynomials. Okay, so your property is the class of low-degree polynomials. And the thing you're testing is, are you low-degree or are you far from low-degree? And again, as always, promise that one of the two is the case. And now the wonderful result here is, which goes back to BLR from 90 and has been improved afterwards, is that you can solve this with a number of queries to the unknown function that scales like 2 to the d plus 1 over epsilon. Okay? So in particular, you can solve this with a number of queries that doesn't depend at all on n, the number of bits that your function acts on. Compare this to the complexity of learning such polynomials. If you think about like a degree d polynomial in n variables, the number of terms is already n dependent, right? So you expect it to scale with n for learning because you have to learn the different terms. And in fact, one can show that the complexity of learning these polynomials is n dependent. It's, I think, like n to the d. So there's a huge improvement here from learning to testing. So this shows you that a testing task can be much easier. And in particular, if you go back to the motivation, so we wanted to test assumptions of learning algorithms. If you have a learning algorithm that has the assumption that the unknown object is low degree, you can essentially, for free, first run the tester to check whether it is low degree. And it's essentially for free because the complexity of testing is so much lower than the complexity of learning. So it doesn't really affect the overall number of samples that much. So in some sense, you can think of property testing as like super fast pre-processing that you can run before your learning algorithm to check that the assumptions that you rely on in your learning algorithm are actually satisfied. Now, this is a classical example, and what I want to do now is show you some quantum examples to give you kind of a feeling for what's been done here in the quantum case recently. And hopefully, these are maybe a little bit more intuitive for you than even the classical one. So the first one is stabilizer state testing. And in stabilizer state testing, the first thing, so it's not always necessary, but when you do anything in testing, it's always good to think about learning as a baseline. Because as we just saw, learning can always be used for testing, so you want to do better than learning. Our baseline in learning stabilizer states is linear in n by Montanaro, and we want to find out whether we can do better. Now, let me be kind of precise about the setup, like I said it before. So your property is the set of stabilizer states. Yeah. Oh, sorry. Thank you. Question.
Explain again the connection between testing and learning.
You mean this picture? Whoops.
Yes, please.
Yeah, sure. So think of my learning algorithm as an algorithm that if you give it something from P, it outputs a good approximation in P. Over here, I give it something in P, so it outputs a good approximation. And I'll check whether it is a good approximation. So I assume that you can estimate distances. Sorry?
So you just have to assume you have the ability to estimate this.
Yes. Distance estimation is usually okay if I give you this classical description, but you're right that it's not always the case. Yeah. Good question. So you need learning plus the ability to estimate distances. In classical property testing, they essentially never mention this because you always have the ability to estimate distances. In the quantum case, it's harder, which is why I emphasize it. Okay, so back to stabilizer testing. In stabilizer testing, our setup is, our property is the set of pure n-qubit stabilizer states. For a distance, you would probably pick trace distance, but most of the literature is in terms of infidelity, so I'll use infidelity. So infidelity is this object here. If you know your Fuchs-Van de Graaff inequalities and so on, it's essentially the same as trace distance, especially for pure states. So don't worry about it too much. Notice that this is not actually a distance. So it's not a metric, which is why I emphasized before it doesn't have to be. Okay, and we have some accuracy parameter, and our access typically is your given copies of this quantum state. Okay. And you want to find out, is it a stabilizer state or is it far? I'll be very brief on this. On Thursday, we'll have Srinivasan give an invited talk on kind of the status quo of learning objects that look a little bit like stabilizer states. So you'll hear much more about this and related questions from him. But let me just tell you kind of what we know. And most of what we know is in this paper by Grosnesamy and Walter. And they proved the following result. So they showed that there's a stabilizer testing algorithm that uses 6 copies. And it accepts with probability 1 if the object is a stabilizer state. And if you're far from being a stabilizer state, then the acceptance probability, it rejects with a non-negligible probability. In other words, your acceptance probability is bounded away from 1. Okay, and you can easily, by repeating this a few times, make the difference between 1 and 1 minus epsilon squared over 4 larger. So you can, with a constant number of copies, distinguish, or I guess technically with like 1 over epsilon squared many copies, distinguish whether it's a stabilizer state or epsilon far. So notice that this is much, much better than learning, because again, learning was linearly dependent on n, but this is completely independent of n. And as I said, I don't have time to talk much about the details. So what this algorithm does is it uses a subroutine called Bell difference sampling. So what you have to do is you look at 2 copies of the of the unknown state at a time, and you measure it in the Bell basis. And you do this for all of these 2 copies, and then there's some kind of non-trivial classical post-processing. But this is the kind of measurement that they use. So we've got improvement from linear to n to constant for stabilizer state testing. There's been a lot of other work on stabilizer testing since. Because I'm already running a little bit behind, I'll rattle through this. And essentially, I'll tell you, don't listen to me, but listen to Daniel and Vishnu on Friday, who will present one of the most recent results in the stabilizer testing literature. One thing that I want to highlight here is that it's also interesting to think about testing with restricted resources. So what I said before is that the best algorithm we have relies on measuring in the Bell basis. So in particular, you need 2 copies of the thing at a time. If I take away that ability, the question is, can you still do something interesting? And it turns out that you can still get an improvement, but it's way more subtle. At least I would say it's way more subtle. Okay. I hope that wasn't too fast. Questions? Yeah. So we're testing in the same sense that I said in the beginning. So you're testing, is it a stabilizer state or is it far from the whole set of stabilizer states? You're not yet finding out which one it is. That would then somehow be the next step where you run your learning algorithm. Yeah, Mark.
Why does it need 6 copies?
Yeah, so this is something that I don't fully understand. It has to do with how you kind of gracefully fail to be a 4 design, I think, in the Clifford group. But I'm afraid I don't understand the details of this. I also believe that I'm not sure whether we actually know whether 6 copies is optimal. I'd have to double check that. Yeah, Manuel. Yeah. Yeah. This is. Yeah. So okay. So the question is there a kind of trade-off between the computational capabilities that you allow yourself? So, for example, whether you're able to entangle multiple copies versus the samples. I'm a little bit hand-wavy in everything that I say. Most of the time, I care more about samples than I care about computational complexity. But you're right. There is this kind of trade-off. In the classical literature, something like this exists as well. So there are computation memory trade-offs, meaning that if I restrict the memory, you will have to invest more computation time. Personally, I think in the quantum case, they're more well-motivated because classically memory is kind of cheap. But they exist, and I'd say they were maybe an inspiration for the quantum results we have by now. Okay. I could do this for a long time, but instead of going through all of the examples, let me just flash the list from before again. So these are the same examples for learning that I gave you before. And for, okay, here I should have put 1 over epsilon squared, sorry. For most of them, we know the complexity of testing, and we know that the complexity of testing significantly improves upon the complexity of learning. So for example, let me just highlight one. If you care about MPS testing, learning depends on n to the third, where n is the number of qubits. This improves to linear. And the physical dimension actually doesn't play a role anymore. So you can get interesting, non-trivial improvements when going from learning to testing in a variety of scenarios. One where I believe we don't actually know it is this result about learning states of bounded complexity. If anybody knows, let me know, but I'm afraid I don't know a result about this. So I spent quite a bit of time talking about states. Let me just illustrate for you that my start with like the abstract definition wasn't for nothing, so you can do more than states. And the other example that I want to highlight is Hamiltonian testing. So in Hamiltonian testing, you're interested in testing properties of a time evolution. And the setup is as follows. So your property is the set of k local Hamiltonians, if we pick locality testing. So what I mean by this is you take your Hamiltonian, you expand it in the Pauli basis, and it's called k local if the only terms with non-zero coefficients are ones where the Pauli weight is at most k. Okay, physically, this just means that the interactions in your Hamiltonian involve k particles at the same time at most. And of course, many physical systems have the property of k locality. But if you're, for example, trying to simulate a target Hamiltonian on some kind of quantum simulation device, you might want to double check that you're actually simulating the right kind of evolution, that there is no kind of complicated crosstalk happening. And in such a case, you might want to test locality. Oops. The distance measure that we're using is the normalized Frobenius norm. I'm not going to tell you why, but it turns out that this is a good measure to use. If you use others, either it becomes too easy or it becomes impossible. So you have to balance it somehow. You can think of this as Fourier being good because it's nicely related to the, Frobenius being good because it's nicely related to the Fourier representations, which are the Pauli coefficients. If you want to know more about this, please feel free to ask. For now, I'll just hide this. You get an accuracy parameter as always. And the access that I'll give you is you have access to the Hamiltonian through your ability to query the time evolution under the Hamiltonian. Yeah?
Sorry, when you say Fourier representation, you mean like the Boolean Fourier representation?
No, I mean this. So you can think of this as like a matrix analog of the Boolean Fourier representation. Okay. So this is now quite different from the state thing we had before, right? Because in states, the only thing you can choose is your measurement. Here, you can choose your input state and the measurement that you perform at the output. So let's take a quick look. And I'll show you one result that we had last year, which is about Hamiltonian locality testing, some technical assumptions. And what we achieve is you can do this with a number of queries that scales like 1 over epsilon to the 4. And even if you care about the total evolution time, it's still nice. And also the post-processing time is nice. And even the measurements are simple. So what I want to illustrate with this slide is, again, you get assuming the operator norm behaves nicely, you have a system size independent complexity. And this is better than anything we know for learning k-local Hamiltonians, where we have, in particular, very bad exponential dependence on the locality itself, and also a somewhat annoying dependence on the system size. Not too annoying, but a little bit annoying. And again, my life is a little bit easier by the fact that you will hear way more about this by John and Daniel on Thursday when they tell you about more recent progress in Hamiltonian locality testing, because they actually improved our algorithm and kind of developed a more generally applicable one. The only thing I want to highlight is I chose locality as an example. It doesn't really matter whether you test locality. There's lots of other properties you could test. Okay. I'll give you one more called passive quantum testing. Passive quantum testing is less physically well motivated than Hamiltonian testing, but theoretical computer scientists like it. So what I've told you about so far is testing properties of quantum things, quantum states or quantum processes. And of course, if you're testing properties of quantum things, you have to use quantum measurement or quantum state preparation. Now I'm going to change the question, and I'm going to ask, what can quantum testing help? How can classical property testing people use quantum physics for help? So this is essentially the same question that we ask in quantum machine learning every once in a while. So how can quantum data representations of classical data be useful? And you can ask the same question in property testing. And here, so the thing you want to test is a property of some function. But the way you get access to the function is using copies of a quantum state that encodes the function in a superposition over input label pairs. This is why it's not so practical. It's a bit hard to argue where you get this from. We could have this debate now, but I think it's been debated to death in the 2000s, so I'll not do this here. And if you're interested in this, I'll be giving a talk on Friday telling you more about the model and what quantum data can buy you here. Yeah, exactly. So the standard motivation for where you get the state from would be QRAM, and then you can debate whether QRAM is realistic. The other potential motivation is you have a circuit that can implement your function, but then you might have a stronger access model. Yeah?
Going back to the Hamiltonian
Yes.
totality test,
Yes.
you mentioned requiring time evolution to deal with this problem with samples of thermal states.
Yeah, very good question. So in Hamiltonian learning, people studied the thermal state side as well. In Hamiltonian property testing, I'm not aware of a paper having the thermal results. I was talking to a few people though, and they have reason to believe that it's very hard from Gibbs states, unfortunately, because you can embed classical problems of testing probability distributions, and these often scale badly. So the main reason why it's different is that in time evolution, people are happy to assume that you can freely choose the time. Whereas if you think about learning from thermal states, people mostly assume that the inverse temperature is fixed. If you allow me to vary the inverse temperature, I can do the same thing as I do for time evolution. But with fixed inverse temperature, we don't know how to do it, and we have reason to believe that it's not possible. Okay, so let me conclude this part of the talk with a challenge that I think is fun. And once you've seen my challenges, you will see that this is a very desperate attempt for me to get the research questions that I don't have time to work on right now out there. But let me nevertheless try. So passive testing, or what classical computer scientists call passive testing, is testing in a way where you can collect data before you even know what you're going to test. That's because data comes in the form of random samples that are not adaptively chosen. This may seem familiar to some of you if you've seen classical shadows and the randomized measurement toolbox. So they have something called measure first, ask questions later, which means that you can, in many of these randomized measurement protocols, collect the data before you know what you're going to use it for. And in classical shadows, this has been extremely useful because once we had the classical shadows protocol, we could reanalyze data that was collected like a decade before. And I think we could do the same for property testing if we understood passive testing better. Unfortunately, so far, we don't really understand passive testing. And a concrete direction would be passive quantum Hamiltonian testing. So the reason why I highlight this question in particular is that we have a starting point. So some of the Hamiltonian testing protocols out there are already passive. That's because they work in a randomized measurement framework. However, not all of them are. And I don't understand which parts can be made passive and which parts can't. So this is a direction that I personally think is a lot of fun. But I've not yet had the time to think about it in as much depth as I want to. Essentially, the question of how far can you push the randomized measurement toolbox in Hamiltonian property testing, I think is a fun challenge. Okay. I will now shift gears a little bit. So if you have questions about property testing, either ask them now or in part 3, where property testing will make a little bit of a return. Yeah, Elias.
I'm just curious about this, because you said that in learning we have scaling and in testing sometimes we don't. Do you have any guess for what the scaling here should be?
In the passive?
Shadows,
Yeah, so this is a good question. So in the examples I've given for kind of dramatic effect, I've picked examples where the system size dependence vanished completely in testing. This is not always the case. The reason I'm really interested in passive testing is because classically, passive testing is a very weak model. In many passive testing results, people show negative results showing that you can't do better than learning. On the quantum side, we now have a few results showing that passive testing can work. And I'm interested in understanding it better. I suspect that you cannot get rid of the system size dependence completely, but hopefully you can make it a mild one, maybe even like logarithmic in system size, something like this. Yeah, please.
To go back to your original point about the workflow and where
Yeah.
there's like breakpoints.
Yeah.
This is one of them. Are you suggesting that before performing learning, we perform testing to
Yes.
check that our data makes sense, and then we perform learning?
Yes. So I think the problem is that I started as a mathematical physicist, and mathematical physicists know how physics works, but then I spent too much time in computer science, so I no longer know how physics works. So I want to actually verify assumptions rather than make them. And this gives, so property testing you can think of as an algorithmic toolkit for checking which learning algorithm you could apply before you run the costly learning algorithm. Exactly right. Okay, so now let me switch gears a little bit. I'll skip this, I think. If you want, ask me later. But so what I told you about was just this very basic observation that learning algorithms rely on assumptions, and that property testing allows you to make these assumptions checkable. And it does so very efficiently, and I gave you a few examples for this. In terms of open questions, we've got Hamiltonian property testing algorithms for loads of properties, but physicists care about lots of other properties that we don't yet know how to test, so I think there's way more to do there. As I said, I think understanding passive testing is a good question. And finally, this is the part that I skipped, but I think taking this perspective, so in classical computer science, people have taken this perspective of testing as pre-processing for learning way more seriously by now. And I think developing this on the quantum side as well would be useful. Okay. So now let me switch gears and go to the second breaking point. So the second breaking point that I want to focus on is essentially a combination of these two. So how can you make sure that learning algorithms are correctly executed and that data is correctly collected? Now here, let's change perspective a little bit. So I claim that this problem is roughly the same as delegating quantum learning. So in delegated quantum learning, you think of one party that, for example, is based at Warwick Quantum, which is a cool interdisciplinary research initiative, but we don't have a quantum computer. So we're a little bit limited in what we can do. So if we want to run quantum learning algorithms, we better ask somebody for help, somebody who claims to have a big working quantum computer and can do cool experiments with them. And then we would kind of ask them questions, propose experiments for them to run, they report the results, and we kind of evaluate our quantum learning algorithms based on the results that they report back. Why do I claim that this is roughly the same as checking whether a learning algorithm is correctly executed? Think of this side here as the learning algorithm that you want to run, which may be costly. Now, your learning algorithm might go wrong. It might go wrong because your device is noisy. It might go wrong because your data is noisy. You don't know. So what you would like to do is, in parallel to your learning algorithm, you would like to run a less costly algorithm, for example, one that uses little or no quantumness, that can check that the other algorithm is running properly. Okay? So in some sense, this is the same problem. Whether you think of me being in Warwick and delegating learning to Google AI, Google Quantum AI in Santa Monica, or whether you think of somebody running a quantum learning algorithm on their chip and in parallel wanting to check that their quantum learning algorithm is running properly, it's essentially the same problem. So the question is, how can you approach this problem? And I'll start with a super quick reminder. If you've not seen this, hopefully you can get the vibe. If you've seen it, it might be a little bit boring. I'll just recap proofs. What are proofs? Probably you've all seen the complexity class NP. So a language is in NP if there's a polynomial time verification algorithm such that for every input x, the element is an element X is in the language if and only if there's a polynomial-sized proof upon which the verifier accepts the input. Okay, so this is one of the two common definitions of the complexity class NP. And there's a quantum counterpart called QMA. And in QMA, it's essentially the same thing, only your verifier is a quantum algorithm, and your proof can be quantum. And because it's quantum, we introduce probabilities, so we have some kind of acceptance probability here. So this is a proof as a static object. It's either just some kind of string that I wrote down on a paper, or it's a quantum state that I give you. Even these proofs are powerful. We believe that NP is much larger than P, and we believe that QMA is much larger than BQP. You can make them even more powerful by allowing for a more complicated perspective on proofs, which are so-called interactive proofs. So for example, there's the complexity class IP for interactive proof. An interactive proof consists of a pair of a verifier and a prover. Both of these are algorithms. And you want to run these two algorithms in parallel, letting them talk to each other, such that if the object is in the language, the interaction accepts with high probability, and we always imagine the verifier accepting in the end. And if you're not in the language, then your acceptance probability should be small, no matter what prover you interact with. So you can think of this as saying, if in your computation anything goes wrong, anything whatsoever, maybe some malicious adversary is manipulating your computation or whatever, you still only have a small chance of falsely accepting. And again, there's a quantum counterpart of this called QIP, which looks very much the same. So the only difference is that the verifier is now BQP, so this interaction can involve quantum communication. And these interactive proofs are even more powerful. For example, we know that IP equals p-space, so the whole class of languages that can be solved in polynomial space, which we believe is significantly larger than NP. So that's how complexity theorists think about proofs. Now, in learning theory, the study of proofs is very recent. It was started by Shafi Goldwasser, Guy Rothblum, Jonathan Schaffer, and Amir Hudayov in 2021. And I think they have one underlying observation that is, to me, super interesting, which is that if you try to design an interactive proof for learning, because machine learning always uses data, you have to take data into account. So in particular, you wouldn't just have a verifier, but you would have a verifier that gets access to data, for example, samples from some function. And similarly, you wouldn't just have a prover, but you would have a prover that gets access to data, for example, queries to an unknown function. This choice of samples versus queries is so that the prover is more powerful. This is a stronger kind of data access. And then you let them interact, and afterwards the verifier should output a hypothesis. And the guarantees that you want and that they kind of require are completeness, which means that if the prover is doing what they're told, then the verifier correctly solves the learning problem. Soundness, meaning no matter how the prover messes up, if the prover messes up, with high probability the verifier will notice and abort the interaction. And finally, they require double efficiency, which means that both the verifier and the prover are efficient. Whether you want this or not, we can debate, but this is their model. So the way they designed the model is very much for classical learning theory. Yeah. Efficient can mean whatever you want it to mean. In their context, it means computationally efficient, so the runtime should be polynomial in the relevant parameters. You could also care only about information theoretic efficiencies, so care only about sample or query complexities. You could also care about communication efficiency, yada, yada, yada. They care about computational efficiency. So how can we make this work for us in quantum learning? So for that, let's take their setting and make it a bit more abstract. So essentially, their crucial observation is to design interactive proofs for machine learning protocols. You should give the verifier and the prover data access. Now, let's just be a little bit more flexible regarding what kind of data access we allow. Here we go. So let's just say the verifier has some oracle that gives them data access. Could be copies of a quantum state, could be queries to a function, whatever. And the same for the prover, and then we let them interact, and the verifier should output a hypothesis at the end. Okay, so this is a very abstract view, but if you view it in this flexible way, you can also make it work for quantum learning, and I'll show you how this works in a second. But before I do, I have a second quiz for you. I know I've not given you a formal definition, but I hope that even without the formal definition, we can think about this quiz. So let's consider stabilizer state learning. You see that I always come back to this example, but you could take any other one. It's just that stabilizer state learning is often easy to think about. So in stabilizer state learning, you're given copies of some stabilizer state psi, and you're supposed to learn a set of stabilizer generators. You could also think of it as just learn an efficient description for the stabilizer state. Now, my challenge for you is give an interactive proof system for stabilizer state learning in which the verifier uses 1 over epsilon many single copy measurements. So what I want is an algorithm where we have a verifier and a prover running in parallel. The verifier asks the prover to do something for them. Afterwards, the verifier checks what the prover did and hopefully correctly learns the unknown stabilizer state. Any takers? My main hint is, even though I write interactive proof, you don't need interaction. So it's even simpler. And maybe think back to quiz 1. So in quiz 1, we had essentially this question of testing whether you're a specific given function or far. And here we want to do something similar, which is why the scaling looks similar. Maybe I should have given the formal definition after all. Okay. So one naive way we could try as a verifier is we could just ask the prover, please solve the problem for me. Just you go do it. I don't want to deal with it. So we ask the prover, please learn the stabilizer state and tell me what you came up with. Okay? So let me show you this. Did I put the verifier on the left or on the right? I'm unfortunately very inconsistent about this left, okay. Okay, so the interactive proof system works as follows. The verifier tells the prover do the job. The prover sends back a description of the stabilizer state, for example, by sending the stabilizer generators. Okay, now I, as the verifier, I've got this purported stabilizer state description. What do I do now? Well, I have to figure out whether the description is a good one. But this is easy. I just measure this 2-outcome POVM, actually PVM. So I just measure this on copies of the unknown state psi. Okay? And we're in essentially exactly the same setting that we had in the case of function testing. So if it's close enough, we'll accept often enough. If this is a bad description, so if it's far from the true stabilizer state, after measuring this for a while, we'll see that it rejects. Okay, so these are the measurements that you're performing is really just you use the description that you're given and you estimate the overlap with the true state. This is one way to do it. You can use a variety of techniques for stabilizer fidelity estimation if you want. Yeah, Mina.
So you're assuming that the verifier has the ability to declare the state?
Yeah. So, yes. So I assume that the verifier has their own data access. Yeah, you're right. Sorry, I should have been more explicit about this. Okay, now this is actually sorry, go ahead.
The prover gives the whole set of this generators or just one?
The prover gives all like a set of n generators for the stabilizer state, yeah. So the prover gives you a full description of what they think is a good approximation.
Sample state, and you could satisfy all the,
Yeah.
you add all of these generators, right?
Exactly, yeah, exactly. I mean, there's different ways of doing stabilizer fidelity estimation. I'm doing a naive one. You could also say, I give you a description of the stabilizer state. You can figure out the Clifford circuit that prepares it. So once you know the Clifford circuit, you can undo the Clifford circuit and check whether your computational basis measurement gives you 0. That you could also try. So there's different tools, but the one that you suggested also works. Okay, now this is boring, and it's actually a boring special case. So it turns out that something called realizable learning is always trivial to verify. Realizable learning is learning where you can achieve a perfect answer. So for example, in stabilizer state learning, if the unknown state is truly a stabilizer state, you can get the right answer. Verification becomes more interesting if there is no perfect answer. So for example, if you're trying to learn a matrix product state representation of a state that doesn't have a good matrix product state representation. So you're trying to approximate the state as best as you can with a given representation, even though you can't do it perfectly. Then this becomes more interesting, and in this setting, there's recently been some kind of a series of works on the quantum side, and I just want to tell you what the scenarios are. So the first scenario that was considered was you have a classical verifier trying to verify what a quantum prover does. You probably, or you might have heard about this in the context of classical verification of quantum computation. What we claim in this paper is that it's different because data is involved. So just running standard verification of quantum computation doesn't do the trick for you. Then in a follow-up work by Ma et al., they looked at a slightly more realistic version of this, where you still have a classical verifier, but your prover is not a perfect quantum machine, rather a noisy quantum machine. And then more recently, with colleagues in Berlin, we looked at what happens when both of them are quantum machines, but the verifier is a much weaker quantum machine in that it doesn't have quantum memory. Okay, so you notice that in all of these scenarios, I'm intentionally making the verifier weaker than the prover so that they can try and profit from the interaction with the prover. Or if you want to think of it the other way around, so that we can check whether our learning algorithm is executed correctly at a cheaper cost than actually running the learning algorithm. And the kinds of results that you can get here are a quantum advantage in what's called agnostic learning that even survives in a noise-robust setting. This is essentially based on a noise-robust version of Bernstein-Vazirani. And then finally, you can also attend the talk on Tuesday if you want to know what you can do with limited quantum verifiers versus powerful quantum provers. So the reason I care about all of this should be challenge 2, otherwise I forgot a challenge. The reason I care about all of this is because interactive proofs are an extremely powerful tool in classical complexity theory. So the help of a prover, even if it's an untrusted prover, can give you quite a bit. In learning theory, it's not as well understood yet how much this can help you. And what I'd like to see is to develop a complexity theory of interactive proofs for quantum learning, because this will tell us which kinds of learning algorithms you can easily, on the fly, verify for being executed correctly. Unfortunately, we're still quite far away from a kind of full-blown understanding of this. We just have a few starting points. But if you like kind of the complexity theory angle on things, then I believe that this is a good area to work on. And the reason I think so is because you can include even other things in your verification. So for example, you can include privacy concerns. So we have essentially the same picture as before. So you have somebody who doesn't have a quantum computer, but who wants to run some quantum experiment. So they outsource it to somebody who has more quantum capabilities available. They run the experiment and give an answer back. And then I publish a paper about it. Now, the problem is that somebody might be eavesdropping on my communication when I outsource learning. And also the other party might just not be trustworthy. So whenever you delegate computation and also when you delegate learning, there are privacy issues to take into account. And you can do this in an interactive proof. So you can do this essentially simultaneously with the interactive proofs aspect. And then another reason to care about this is that in the classical world, there was a recent work that demonstrated the surprising power of interactive proofs for learning. So in particular, they gave doubly efficient interactive proofs for learning heavy Fourier coefficients and agnostically learning AC02 circuits. If you don't know what these terms mean, it's not so important, but classical computer scientists really care about these things. So this is related to something called the Goldreich-Levin algorithm, which was like a big deal in the 80s and has been important ever since. And this is a complexity class that classical learning theorists just don't know how to learn. They really don't know how to do it. But if you give them interactive proofs, they suddenly can. So that showcases the power of these things. And then if you go even one step further and you drop the double efficiency requirement, so you allow the prover to be like wasteful and inefficient, they show that suddenly you can learn all of P/poly, which is like an absurdly large class. So it's like polynomial time implementable functions with polynomial-sized advice. And this thing is like extremely non-learnable. So if you don't have the help of a prover, you cannot learn this. But with the help of an unbounded prover, they show that you can do it. So this hints at a complexity theory of interactive proofs for learning. But I think it's not fully developed on the classical side, and on the quantum side, we have barely anything. Okay. Yeah. Yeah, good question. So I don't care so much about the precise execution. I care about whether the thing you produce is good. So I care about whether the learned model is a good approximation. If you get there in some weird way, I will still accept it as long as the model is good. Okay. Now, let me get to my last section because I don't have that much time left. We'll go to the last part of the pipeline. So we've tested the assumptions and inputs. We've tested the execution. Now let's test the outputs that come out of a learning algorithm. And we'll do this, again, using property testing, but we use a specific case. And maybe one reason why you should care about this is because not all learning algorithms that we run come with provable guarantees. Sometimes you have heuristics for why learning algorithms should work, but maybe you want to check afterwards whether the heuristics were justified and whether they actually worked. So that's where testing the outcomes of a learning algorithm becomes useful. And we do this using identity testing. So this is the picture I showed you before for property testing. Now, identity testing is a very simple special case where the set in the middle is a single point, and then we put a ball around it. Okay? This is called identity testing. It's sometimes in other literature called certification, but essentially the same thing. So here's the formal definition. It's exactly the same that we had before, only that I made the set P a single point. Okay, so this is the question of identity testing. Are you equal to an unknown, to a target object x0, or are you far from that desired object? Now, you should be more tolerant than what I'm showing you. So what you should actually do is tolerant identity testing. So testing whether you're close or far. The reason for this is that a learner rarely outputs exactly the right function or state. It often outputs an approximation. Unfortunately, this is a subtlety that I don't have time to talk about. But in principle, you should do all of this using tolerant testing, which goes back to Parnas, Ron, and Rubenfeld. That I ignore this is not without loss of generality, but it's for time-constrained reasons. So I'll go with standard identity testing. And this has been studied quite a bit already. So in testing quantum states, we know the complexity of what they call state certification. So recall that learning an n-qubit state takes you 4 to the n over epsilon squared copies. So how efficiently can you test it? Well, our setup for this would be that you have some target state rho 0, and you want to test whether it's that state. And let's say you want to test whether it's that state or whether it's epsilon far in trace distance. And you do this given copies of the state. So this question, in some sense, has been fully resolved by Badescu, O'Donnell, and Wright in their 2019 paper, where they showed that the complexity of state certification is 2 to the n over epsilon squared. So it's still exponential, but it's better than state tomography, right? It's 2 to the n rather than 4 to the n. And if you assume something about the rank of the state, you can do better. So you can do this in rank of rho 0 over epsilon squared many copies. This is a worst case result. Recently, there was a fun improvement by O'Donnell and Wadwa that makes this kind of very specific. So this bound works for every state rho 0 that, so here it works for everyone, this works for everyone that has this specific rank. But rank shouldn't be the only thing that matters. So what they show is that actually you can get you can get tighter bounds that take into account how far you are from maximally mixed. So in some sense, the state that's hardest to certify is the maximally mixed state. And the farther away you are, the better your bounds are going to get. And I'm lying a little bit here, but essentially their result scales with the fidelity between your state and the maximally mixed state. Now, let's do our final quiz. So I want to look at one special case here, which is identity testing for a single pure n-qubit state. Okay, and our distance measure now is again infidelity. We have some accuracy, and they give you access to copies of the state. And what I would like us to figure out is how can we solve the corresponding testing problem using 1 over epsilon samples. Okay, samples means copies, sorry. Any suggestions for how to do this? So you want to test, is it psi or is it something far away from psi? Yeah. Exactly, you do what I wrote on the board. So you just measure the 2 outcome POVM that has like the projector on psi as one of its elements, and the orthogonal projection onto the complement is the other one. If your unknown state is psi, this will always accept. If your unknown state is far from psi, you have like a reasonably good chance that it rejects. So just repeat it a few times and it's going to reject.
It should be psi 0, right?
Oh, sorry. Yeah. Thank you. Should be psi 0 now. Okay. Now, what's bad about this algorithm? So why is this a bad thing to do? Any suggestions? Sorry? Can you say this a bit louder? Yeah, exactly. So this measurement that I described here could be very hard to implement. For example, if psi is a state that requires a very deep circuit to prepare, probably the way you're implementing this is you're undoing the circuit and then measuring in the computational basis. But that means you have to like apply a very deep circuit. So this is very bad in that regard. It's kind of computationally heavy. So because of this, recently there was a push to understand how to do this with simpler measurements. And there's a very cool work that focuses on doing this from single qubit measurements. So notice that this is not single qubit unless psi is like a simple state. And so Huang, Preskill, and Soleimani-Fa showed that for almost all pure states, you can certify them using single qubit Pauli measurements on quadratically many copies. So this is worse than the bound that we had before, but it's surprisingly still very efficient in system size. And in follow-up work, it was shown that this is not just almost all, but it's all if you allow yourself adaptive single qubit Pauli measurements. They can do a little bit better, but this is essentially contained in the previous results. So this is another example where the testing task becomes interesting only when you have restricted abilities. But surprisingly, even with very restricted abilities, namely single qubit measurements, you can do it. And this, again, is kind of part of the randomized measurement toolbox framework. And to me, it was surprising that the randomized measurement toolbox can actually do this. Oops. And what I want to highlight is that now that we have the question of identity testing, you can ask this in lots of other contexts. So for example, you could ask it about Hamiltonians. So this would be checking, for example, whether your quantum simulator is simulating the right evolution. Yes, please. Yeah. Yes. So you in identity testing, you always know the unknown object that you're trying to test identity with. They don't require a full classical description. They've got a slightly weaker model, but for today, let's maybe think about it as full classical description. So you can do the same thing for evolutions to, for example, figure out whether your simulator is implementing the right Hamiltonian. So here, we have some results in Hamiltonian learning, but they scale with system size. And now you want to check whether your unknown Hamiltonian is equal to some h0, where we again measure distance in Frobenius norm, and I give you time evolution access. And here, we also have some recent results that give us what's called Heisenberg limited scaling, so 1 over epsilon scaling in total evolution time. And if you want, you can get rid of the inverse time evolution that they use for a simple subclass of Hamiltonians. So also in the time evolution case, we've started to look at identity testing. I could list more examples here. I focused on the Hamiltonian case because that's what I told you about before. These results both hide in the complexity essentially assumptions on the boundedness of the Hamiltonian, either on the operator norm or on the one norm of coefficients. I'm not going to go into that. And here, I think that to me, an important open question that we don't know the answer to yet is in this result here. We use backward time evolution. So we assume that you can invert time evolution as well. I'm not a huge fan of this assumption. So it's a common assumption in many quantum algorithms that you can implement U and U dagger. Personally, in Hamiltonian evolution, I think it's maybe not always a good assumption. So I'd like to get rid of that. And in that paper, we got rid of it, but only for a very restricted class of Hamiltonians. So I think a good challenge is to figure out where in between does the middle ground lie. So what is the actual complexity for identity testing k-local Hamiltonians with only forward time evolution access? Because what this means is that if you have a Hamiltonian learning algorithm that, for example, helps you transpile a Hamiltonian evolution onto a simulation device, and if that simulator can only simulate forwards in time, you can still check whether the simulator is a good one. If you tell me that many simulators can do inverse time evolution as well, I can come up with other motivations for this question, but that was my initial one. And so this was about certifying the outcomes of learning algorithms. I want to highlight one other really cool classical paper that I think the quantum community should take some inspiration from, which is by Amit Goldwasser, Paradise, and Rothblum, about self-proving models. So I've shamelessly stolen their figure. So this is the scenario that they consider. You might recognize it from the interactive proof that I showed you before. So what they want is that a self-proving model can convince a verification algorithm that its output is correct. So think of a large language model that doesn't just tell you how it would continue a sentence, but it also gives you a reasoning for why it thinks that this is a good continuation of a sentence. And what they develop in this paper is both a theoretical framework and numerical implementations for a specific task. So what you imagine is you have a verification algorithm for some ground truth, and then they define what they call the verifiability of a model. So they define the verifiability as the probability that the model successfully convinces the verifier. And what they show is that you can train models to achieve good verifiability. And they show this also in terms of numerics. And I think the quantum community should take some inspiration from this so that we can make our learning algorithms verifiable, meaning that they, in addition to learning the unknown object, come with a reasoning for how they arrived there. Given the time, I'll skip the summary. I'll thank you for your attention.
Please do the summary.
Okay.
Go on.
So this last part, I told you that, so we had property testing in general for assumptions, but you can use identity testing to check outputs of learners, even if you haven't checked its assumptions. This can still be much cheaper than learning, and for example, in the Hamiltonian case, we have some recent progress. However, I think it's still quite limited. So we have it for a few state classes and a few process classes, but not actually for many. And yeah, finally, as I said, I think self-proving quantum learners would be a really cool direction to push quantum learning theory. And I think that was everything. Yeah, thank you very much. And if you have questions, please go ahead.